the Zariski topology. But before that, we will start with the definition of algebraic sets. So let us consider K to be an algebraically closed field. So let K be an algebraically closed field. A subset V of Kn is called an algebraic set if this V is some common zero set of a bunch of polynomials. I mean, if V is the zero loci of the set of polynomials in S, where this S is a subset of the polynomial ring over K. Now these algebraic sets, they have the following properties. So let us state these properties in a short lemma. So for an algebraically closed field, say K, we have the first item which states that the zero set of the zero polynomial is the whole space, the affine space Kn. Second item, the zero set of the whole polynomial ring. So this is an empty set. For the third item, we have this is the zero set. So the zero set of n-fold product of the sets S1, S2 through Sm. So this is actually the union of the zero sets of these SIs. And finally, for the fourth item, we have the zero set of the union of S alphas, where alpha is in some index set. So it is actually intersection of the zero sets of S alphas, where the intersection runs over the same index set. So let us prove this lemma. So we have the first item. So this follows trivially because zero polynomial evaluated at any point of Kn gives 0. So clearly the zero set of the zero polynomial is Kn, and the reason being, so since zero polynomial evaluated at any point of Kn gives 0. So that means the zero set of this polynomial is this whole space. So for the second item, this is also trivial. I mean, because this polynomial ring over here, this contain the units of kn. So I mean the elements of k. Now so let us write this down over here. So this is also trivial, since the non-zero constant polynomials in this polynomial ring in n variables, so they do not, I mean they do not vanish at any point. So they does not vanish at any point of kn. Now for the third item, we have we have this s1 dot s2 through sm. So this contains the polynomials of the type f1 dot f2 dot through fm, where fi is a polynomial in si, and si is subset of the polynomial ring k x1 through xn for all I equal to 1, 2 through m. So let us now to prove this item over here. So we generally prove this set is a subset of this set and vice versa. So let us assume there is a point in the zero set of so let the point lambda 1 through lambda n be a point in si, not si, the zero set of si. So if this is the case, then each polynomial in si vanish at this point. So therefore fi evaluated at lambda 1 through lambda m, so this gives 0, and this is true for all fi in si. So for all fi in si. So if this is the case, so this implies if I take in the polynomial f1 through, so here we forgot to mention that this is for some I equal to 1 through m. So this is not m, this is n, because these this has to be a subset of Kn, I mean a point in Kn as well. So this implies that f1 through f m evaluated at the point lambda 1 through lambda n, so this is n over here, so this gives 0. So thus the point, I mean thus the point lambda 1 through lambda n belongs to the 0 set of the n-fold product S1 through Sm, or in other words this implies so this further implies that the 0 set of Si is a subset of the 0 set of this set S1 through Sm for all I equal 1 through m, and hence the union of these sets is also a subset of this 0 set of these polynomials. So we are done in one way. Now to prove the reverse inclusion, so now let we have a point, say z1 through zn in the 0 set of S1 through, which is not S1 product Sm. So this means therefore for all f1 f2 through fm in the set S1 through Sm, the polynomial evaluated at this point is 0. I mean f1 through fm evaluated at lambda 1 through lambda 1, so this gives 0. So this implies that, so if this is the case, that means there is some say fj, while j is between 1 and m, such that fj evaluated at this point is 0. So this implies fj evaluated at lambda 1 through lambda n is 0 for some j, while 1 is less or equal to j and j is less or equal to m. So that means this lambda 1 through lambda n is a point of 0 set of I mean this shows that lambda 1 through lambda n, this is actually some point in the 0 set of Sj, and Sj is the subset of the union of elements of the form Z of Si. So hence 0 set of S1 through Sm is contained in the union of the zero sets of SIs, where I varies between 1 and m. This proves the item third. So finally, for the item, for the last item we have, so we have the item 4 here. So we have to prove the zero set of the arbitrary union of these S alphas is actually the intersection of the zero sets of S alphas. So note that a point, say lambda 1 through lambda n, is a point in the intersection z of S alphas if and only if for each alpha and for all f in S alpha, f evaluated at lambda 1 through lambda n is 0. So that means when this is true for each alpha and for each f in S alpha, that means it is true for the set of all polynomials in all S alphas. So that is if and only if f evaluated at lambda 1 through lambda n gives 0 for all f in the union of the polynomials in S alphas. So that means, and this is true if and only if f is if this is true if and only if this point z1 through zn is a point in the zero set of the common zero set of the polynomials in this union. So this proves the item 4. Now we have a remark here. So this, the above lemma implies that the set Kn becomes a topology, a space, topological space if we declare algebraic sets to be closed sets. So this topology is called the Zariski topology on Kn. The set Kn together with this topology is called the affine space. Let us first mention here the definition of so if we have, so let X be a non-empty set. So then the collection, say fancy T of subsets of X is said to be a topology if this fancy T satisfies the certain actions. So if T satisfies the following conditions. So the condition first is that the empty set and the whole set X, they are the elements of this collection T. Second, if we take any sub collection of of the collection T, the union of that collection T has to be an element of T. In other words, T has to be closed under arbitrary unions. So second is that union of T alphas, where alpha is in some, let us call these U alphas, where alpha is in some index, let's say lambda. So this has to be an element of T where U alphas are in T for all alpha and lambda. And finally this T has to be closed under finite intersections, i.e. if we take the intersection of say n elements of T, then this intersection has to be an element of T. So where ui is in T for all I equal 1 through n. So then we call these U alphas, I mean the elements in T, we call this elements in T the open sets. Now we can define the same, so we can define the same topology on X in terms of closed sets. Now we call a set, we call a set closed. So V is closed if and only if it is, I mean if and only if the set V minus X minus V is open. So in that case, these I mean the first action will the first action becomes the set X minus the empty set and X minus X are the elements of T. So X minus empty set is X and X minus X is empty set. So first condition remains unchanged. So to define the same condition, I mean the same three conditions in terms of closed sets, the first condition remains as it is. The second condition says that using De Morgan's laws that T has to be closed under arbitrary intersection of closed sets, and condition third is that T has to be closed under the finite unions of so let us write this down. So first condition becomes X minus empty set and X minus X has to be an element in T. Second becomes X minus the union of these U alphas, which is the intersection of X minus U alphas. So this has to be an element of T. So if U alpha is open, then this set over here is closed. So this says that the T has to be closed under arbitrary intersections of these sets, I mean closed sets. And finally for the third condition we have X minus the finite intersection of open sets Ui's, which becomes, using De Morgan's laws, which becomes the union of finite union of these sets X minus Ui. So note that Ui is open, so this is closed set. So the condition third becomes this fancy T has to be closed under finite unions of closed sets. So if we declare the algebraic set is to be the so let us make this a remark here. So the above lemma implies that the set say k to the power n becomes a topological space if we declare algebraic sets to be closed sets. To be closed sets of the space. And this space is called this topology on Kn is called the Zariski topology. On Kn, and the set k to the power n along with this topology is called affine n space. So let us make a definition here. So one can note here the 4 items which we proved above in the lemma says that Kn contains so suppose if this is the set X, then Kn contains the Zariski topology. Since this is Kn is algebraic set, this empty set is algebraic set, so that means the empty set and the set Kn being algebraic sets are subsets of they are the closed subsets of the set Kn, and the finite union of closed sets is also closed because this is an algebraic set over here. So since we declare the algebraic sets to be closed sets, so that means the finite union of closed sets is closed. And finally the item 4 over here says this set over here, this is also an algebraic set, and hence the arbitrary intersection of closed sets is closed set. So that is what we mean by this remark over here, that is if we declare these sets to be the so if we declare the algebraic sets to be the closed sets, then we have a topology on Kn. So the unique topology on An, so we forgot to mention here, this is called an affine n space denoted by An. So the unique topology on An for which the closed sets are precisely the algebraic sets, for which the closed sets are precisely the algebraic sets. Of An. So is called the Zariski topology, is call the Zariski topology on AN. Now we have the picture. The picture now goes like this. So we have the geometric side and we have the commutative algebra side. So here we have the polynomial ring K x1 through xn, and here we have the affine space AN, which is the space Kn with the topology, the Zariski topology. So if we choose S to be a subset here, then corresponding to this set S, we have this zero set S here. Now subsets in K, subsets in this polynomial ring over here are not nice objects, because if S contains a unit of this polynomial ring, if S contains a unit of this ring over here, then this set over here is always empty. So if a unit goes inside S, this ZS becomes empty. So instead of taking subsets in Kn, it is better to take the ideal generated by such subsets, and we know an ideal blows up to the whole ring if a unit goes inside it. So remark, so if Z of S is non-empty, then even if the set S in the polynomial ring K1 through the polynomial ring in n variables over K is infinite set, the ideal generated by S, the ideal generated by S is still an ideal which is finitely generated. And the reason being, since K is Noetherian, by Hilbert-Bess's theorem, this is Noetherian, and hence every ideal in this polynomial ring is going to be finitely generated. So this is a finitely generated ideal, where these Fi's, they are just elements of the polynomial ring. So this is an exciting thing about this this interplay over here between these two sets. So if S is an infinite set, then the ideal generated by S is still a finitely generated. Now I forgot to mention over here, the ideal generated by S means the smallest ideal which contain S. In other words, it is the intersection of all ideals, say ideals I, which contain S. Or by using definition, this ideal generated by S is the set of all linear combinations Fi, Gi, where I goes from 1 to n, and Gi is an element in the polynomial ring K x1 through xn. So now it is better to take instead of set S, it is better to take the ideal generated by S, and then if we look at the zero set of the ideal generated by S, so this this is same as the zero set of the this finite set F1 through Fm, because any common zero of these polynomials will be a zero of any element in this polynomial ring, because if these polynomials f1 through fm vanish at some point, so does their linear so does this element. So that means instead of this set S, it is better to take the zero set of the ideal generated by that set. Now we have one more, we have something more to mention here. So let us call these remarks. So first one is the Zariski topology on the Zariski topology on A1 is simply the cofinite topology. Because this set over here, this is not finite. This cofinite topology cannot be that discrete topology, because this set being infinite. So which is not discrete topology. Since A1 is an infinite set. Now let us quickly mention here what do we mean by cofinite topology. So let us take a set X and T, let us write here COF by, which means cofinite. So then an element U is open in U is in the element COF. An element U is open with respect to this topology if U complement is a finite set, or U is equal to X. So the complement of any open set is a finite set, or the set X itself. So with respect to Zariski topology, a set, now we have this situation over here. So we have the polynomial ring in one variable, and we have the affine space A1 here. So if I take any set S here, which will be K being a field, so this is a PID, principal ideal domain. So the ideal generated by S will be an ideal generated by the single element F. Now F is a polynomial in this ring, so this polynomial has finitely many zeros. So the algebraic set related to this polynomial is a finite set. So with respect to the Zariski topology, the closed subsets in this case are the finite sets, which is precisely this topology over here, the cofinite topology. And we have second remark over here. So polynomials, polynomial functions, polynomial function on A(n) are continuous with respect to the Zariski topology. On K, which is the affine space A1. So one can note here, so if we had a polynomial ring in n variables, so any polynomial over here can be identified as a function from the affine space Kn to K, where f takes the point A1 through An to the point which is given by the polynomial f evaluated at this point. So that means with respect to this topology over here, every polynomial function on An is continuous function. So we'll discuss this in detail, because every polynomial pulls back on closed sets to closed sets.